450,000 kilowatts. I thought it might be fun to go outside and trace the steam from beginning to end in the production of geothermal electricity. We've seen the steam above ground. In a few minutes we'll consider where it comes from below ground. But what great hospitality of the Italians here to open the pipe and let us see the energy in the pipe. As the steam leaves the well, or the pipeline as we just saw, and comes indoors, it is used to turn turbines which twist wires inside of a fixed magnetic field, thereby generating the electricity. Here we're seeing one of the turbines with its cover removed, and you see some rags laying there which are being used to clean the turbine blades. The minerals dissolved in the steam don't attack the turbine blade, but instead deposit on it, and it makes it necessary to clean each turbine once about every 2 years. In other areas of the world where this is a much more severe problem, a heat exchanger is used to isolate the turbine blades from the corrosive vapors. After the steam leaves the turbine, it goes out through a cooling tower reminiscent of nuclear cooling towers in the United States, and the temperature is left escape through the cooling tower, and the steam, in terms of cooled water, is re-injected in some cases at temperatures at about 75 degrees centigrade. Here we see some of the pipes collecting steam from across the countryside from various wells and bringing them to the turbine house where the centralization of the power generation can take place. So we have seen the steam come up from the ground, be used to generate electricity. Then the transmission leaves the plant and the water is recondensed to steam and put back in the ground. Here in the museum we realize that not only was the development of geochemistry and geothermal electricity a first at Larderello, but indeed the very history of drilling is, as being shown here in these models, developed at Larderello. These first two drills were in fact hand-turned, and it's amazing to believe that they could drill with only hand and shoulder and grease power, elbow grease, to depths of a couple hundred feet. You see the dates here. In the mid-1800s, there was still not a motorized drill. They were using tools and developing coring tools, actually here, for the rest of the world.
As early as World War I.
It was still pretty much hand drilling, and only after
World War I.
do the drilling platforms here, as shown by the dates, begin to look like modern drills with elevated platforms, clutches and motors, and no longer using just back and muscle power, but using engines to turn the drills. The idea of drilling history here at Larderello is also quite true. The first 100 or so years then at Larderello, the main emphasis was on drilling and exposing new wells to extract vapor so that the vapor could be used to extract boron from the vapor. Looking back down the hall of history here, just again to remind ourselves that the whole history of drilling was developed at Larderello. With the production of the vapor and the extraction of the boron, a great industry had been started by Count Larderello and now bears his name. This graph shows 100 years of activity at the Larderello site, starting in about 1840 and going down to about just before World War II, 1938. There are three different curves being shown here in the 10-year increments of data, And the main thing at this end of the graph is how steep the rise was just before World War II of the production as indicated by the steepest line, which is total steam output. The line decreasing from the upper left to the lower right in steps is the actual tonnage of boron being extracted, and the lower curved line starting in the left and going over to the right gives you some idea of the amount of steam that was actually being tied up with boron production. In World War II, as the Nazis retreated, they mined the wells and blew them so that the Allied powers got nothing from the wells. So production stopped at the end of World War II. The black board is a squid cutting board. Bait board for the boat. I asked Sue Brantley what she wanted in the format, and she doesn't know, except she wants something she can play on her computer. So. Exact form of tools which are being used, extractors, percussion taps, screw extractors, paddle wheels, and some of the early hand elbow grease tools are shown here also. So we've talked about this, that drilling was in fact developed here at Lardorello and the geothermal fields. The other kind of thing that was developed was the knowledge, the engineering knowledge of how to handle blowouts and how to handle wells that were drilled that produced a tremendous pressure. In the early days, the holes that were drilled, the sidewalls were not cased. That is to say, they were not lined, and a pressure buildup occurred from the entire length of the hole. When the pressure got too large, a blowout would occur, such as this one in 1923. As a result of these kinds of accidents, much was learned about how to contain this kind of pressure in either a geothermal or a natural petroleum well. Casing was put in so that the production site of the well was only the last few feet. And furthermore, T-valves were put in at the top of the well where one would drill the stem of the T and have valving off on both of the sidebars of the T so that some kind of pressure containment or pressure relief, as the case needed to be, could be achieved without losing control. Thus, we've looked at some of the history here at Lardorello. We've looked at how a geothermal plant works here, a model just to remind us of all that we've seen thus far. But we've left hanging one important question, and that's, how does geothermal energy originate? Here, with the use of a 1980 cartoon off of the cover of the Transactions of the American Geophysical Union publication, we can look at some of the various features of geothermal energy. A typical geothermal well is depicted here, and it involves these jargon word things called aquatards, aquifers, and radiogenic places in the crust of the earth. It's well to think a little bit more about what these words signify. In the sense of an aquatard, we're talking about, or an aquifer, the Latin gives us some idea that we're talking about the movement of water through layers of the crust of the earth. The aquatard means a layer which retards the movement of water. An aquifer means a layer which in fact allows recharge from rain and so forth and water to pass down into the crust of the earth into an aquifer, the vertical motion of that water then may be retarded by an aquitard. This is sometimes referred to get the idea across smoothly, as an aquifer sandwich, where there would be a porous layer capped with a non-porous layer. The other piece of the geothermal generation is, what is the temperature of the earth? And as indicated in this cartoon, it may be in a steady state earth 30 or 60 degrees on these isotherms. But when we get in proximity to a radiogenic heated portion of the basement complex, that temperature may be driven up by the radioactive heat that's concentrated in such a plutonic mass. The heat then causes a higher temperature closer to the surface than would otherwise be there in a steady state earth. And that is the idea here, that one is able to tap 60 degrees centigrade, perhaps at only half the depth that it would be out in a steady state earth, away from the radiogenic heated area. The idea that this well would perhaps be very difficult to find because there's no surface expression of it would involve some geophysical mapping and investigation. On the other hand, this other type of well, where there is vertical cracks in the aquitard, steam may be leaking to the surface, vertical recharge may be taking place more or less constantly, and this kind of geothermal area, again involving a radiogenic heating mass below it, would be very obvious. There would be natural steam emanating from cracks in the ground, and therefore would be much easier to find. Both types of geothermal, both the open and the only by mining, have been discovered here at Larderello. Here's a picture showing some of the natural steam leakage across the valley, and zeroing in on some of the geologic formations that are involved here. You can see such things as dolomite, calcite, sandstone, conglomerate, different types of rock porosity being involved, so that there is the possibility in the valley below Larderello, not surprisingly, of the so-called aquifer sandwich of aquitards and aquifers. The ages, you may have noticed, are from recent all the way back to Triassic, about 200 million years ago. So Mother Nature took about 200 million years worth of crustal accumulation here to set the stage for the possibility of geothermal energy. Right in the center of the screen, you can see that there are also some faults which cut down across the green dolomitic materials down into the underlying red aquifer, in this case a sandstone. In some places of the world, the green dolomites would be considered aquifers in their own right, but everything is relative. And here at Larderello, the dolomites are in fact the aquatards, far less porous than is the underlying porous red pinkish sandstone showing here, which is the site, the target for the drilling of the wells here at Larderello. And the faults themselves, you see, have the ability to bring natural leakage of steam back up to the surface, as is shown here in a panoramic view of the Larderello Valley. Before we leave Larderello, having answered most of the questions in a general sense about geothermal power, it's interesting to just reiterate, here we're looking at the plant manager in 1904 and the very first generator using Larderello natural steam. It was capable of lighting about a dozen 20-watt light bulbs. That's hard to have much scientific excitement about in this day and age, but in 1904 Edison had just discovered the light bulb, and it was indeed very significant. The idea that there are suburbs of Naples involved in this story behooves us to look at a larger scale map.
As we have just seen in this tape, the Italians have the historic claim for the development of geothermal energy. Here in the Naples area, there's quite a few state parks and known thermal areas. In the Vesuvius central portion of the Naples harbor, and over here at Pozzola Solfatara, so that it's a foregone conclusion that the electric industry of Italy would try to drill into some of these thermal areas.
The electric industry in Italy is nationalized and works together with one of the petroleum companies, AGIP, and before the potential dangers of this inflation, a very large blister in the crust of the earth here in the suburbs of Naples, perhaps growing to as high as 30 feet high over a 5-kilometer diameter area in just 10 years, before that blister was fully recognized, there was an effort made, for all good reasons, to drill into the heat sources in the Solfatara area and produce, as we're seeing here, actual local, right in the suburbs, of metropolitan Naples, geothermal electric production. You're seeing the steam separating towers, the overflow lake for the recondensed water, with the idea that the produced steam from such a well could be used to turn a very local dynamo and generator. And it has, of course, the added attraction that it may be taking some of this extremely high heat so shallow in the crust and using it up in the production of steam, thereby, if you will, defanging some of the danger of high temperature in the shallow crust area. 13 such wells were drilled, and it's now a very strange and complicated legal question as to whether these wells should even be touched. It's kind of a no-win situation. If the companies that own these wells touch the well and something happens either to the inflation or the deflation of the blister, they undoubtedly would be sued by the people involved in the inflation and deflation. What about this inflation and deflation? It has actually broken up many government buildings. It has almost a daily occurrence of a news item in the newspaper, as you're seeing here in the Naples newspaper. $3 million for the exploration of the ground around Monte Ruscello in the Solfatara area. Schools have caved in. Doors won't close in homes. Government buildings have had to be evacuated. This inflation is a very real thing, and it involves people, so much so that the Italian government has started running fire drills, if that's not the wrong word to use, on how an evacuation of the 2 million people who live in the blistered area would have to occur if the blister starts to become very catastrophic. Here, in fact, is Dr. Marcello Carapezza convening the Society of Italian Mineralogists and Petrologists for the exact purpose of discussing what the scientific sensibilities are of what should be done about this blister in the Solfatara area. Some of the things that the symposium, the convention, in fact, discussed were the kinds of things that we've just been seeing out in the field, having to do with the suburbs both to the northwest and the southeast. It was viewed to be essentially such an important meeting that there was simultaneous translation for the various attendees. Some of the volcanological experts from Russia, Japan, and other countries of the world were called in for their advice on what the best guess is that might be happening to cause this inflation, this crustal disturbance in the Naples area. Here are some of the translators. Again, one of the staff members from the University of Palermo discussing his results on some of the types of gas analysis that you saw being taken in the large glass tubes.
So at this meeting, this whole idea of exergy, it's very clear that to make Naples suburbs safe, to take some of the steam pressure out of this blister that's inflating the crust under Naples, there should be some kind of withdrawal, and if we could turn that withdrawal into a good of its own right to make electricity geothermally, it would be very wonderful. The temperatures and pressures are showing on the screen now as to how hot the steam is underneath the Naples suburbs, and the gas analyses that were also being taken to be sure that there were not poisonous gases coming.
And we see that as almost daily basis there are changes in the chemistry of the gas going on in the inflation area at Solfatara. This again is a source of great concern. Why is the situation so unstable? Why are there earthquakes? Why are these daily spikes?
The Pune geothermal venture is a geothermal electric production of over 30% of the Big Island's kilowatt hours of electricity. What they have done is drill into the flanks of Kilauea volcano, the very large volcano on the island of Hawaii. They're down about 10,000 feet, and they're bringing up extremely hot steam, but it has, just as we heard in Naples, some bad effects perhaps as well, or at least undesirable effects, because it's coming up charged with hydrogen sulfide. At Larderello, the boron was a good thing. Here, the hydrogen sulfide has to be neutralized and chemically extracted because it would be too corrosive on the turbines. By now, you should recognize the blue drill stem laying on the right of the pile, and their logo for their company, the rotor on their sign, as part of the turbine for geothermal steam electric production. Just as in Naples, where there was some danger to the suburb whether they took the steam out or left it in, the neighborhood in which the Pune geothermal venture has been constructed, as you see on the screen now, was on the south coast of the Big Island, some really multi-million-dollar homes, and yet the rest of the island needs the power, and the impact of trying to make electric power out of the side of a volcano. So again, this theme of exergy. In the chemistry of the plant here, they have to add potassium hydroxide to the steam as it comes up and cause an oxidation and removal of the sulfur, and then they can pass the hot steam over the turbines to make electricity. Interestingly enough, this whole operation is owned by Baltimore Electric, and so the production of the electricity is, again, owned by an electric company. You see here some of the separation towers where the particulate matter and the steam, and perhaps flashing the steam to a larger volume, so some of the dissolved material is left behind and doesn't end up precipitating on the turbines. The control of the chemical engineering here is all done by remote and computer, as we'll see. Here in the control room, we see that everything is computer operated. The chemical engineering of neutralizing the steam, of letting it flash to lower pressure, and watching all of this by remote computer control. The operator here of the power station. Again, 30% of the electricity in the Big Island of Hawaii coming from about 3 wells, at least that's what they had at the time this footage was taken. And because of the need for more electricity, ever more electricity in society, the Pune venture was in the process of 2004 drilling several more wells into the flank of Kilauea. You get some idea of pressure gauges and temperatures of the chemical engineering process, and then as the steam condenses back to cooler water, it's re-injected back down the well, perhaps to recycle on another day. In Iceland, the Reykjanes Peninsula, just now being pointed out, where Reykjavik is, the main harbor and airport and so forth, is the coming up of the Mid-Atlantic Ridge, and it comes into about mid-Iceland and splits into two, so it's in there essentially like a Y shape, like that. Here in Iceland, the source of heat near the surface is the fact that Iceland straddles the mid-Atlantic ridge, an upwelling of heat from deep inside the earth which brings volcanism and forces lava out to form a ridge that runs the entire length of the Atlantic Ocean. So here the idea of getting the energy to the surface is not as difficult. So Iceland perhaps is lucky that they do not have exergy problems. However, exergy here takes another direction. It's very costly, and only because Iceland is so devoid of other forms of available energy, perhaps just here and there some hydroelectric from flowing water, can there be the sense of spending the money. The Iceland population is so small that their tax base has a hard time coming up with $1 million or so or more even for drilling each of the wells, the top of which we're seeing at this wellhead here. The expertise with which the Icelandic and the Italian governments have developed geothermal energy becomes something that they themselves export by training second and third world country people around the world. And so the experience that they're gaining with how to convert geothermal energy into electricity is something that within the next generation may become much more common. Continuing in our theme of exergy and societal need for energy, here we are having jumped into the Kamchatka Peninsula, hangs down off of Siberia, very remote in Russia, with very few people currently needing electricity. The whole development of the Kamchatka Peninsula awaits the development of electricity. Lots of mineral wealth there, but no power for the people even to live. So here, guests of the Russian government, we are visiting one of their first geothermal power plants in the Kamchatka Peninsula. We saw the pressure gauge fluctuating as the steam pressure in the line is jumping because they are flashing the steam to make some of the temperature drop occur, and many of the dissolved minerals that may be in it precipitate inside of a chamber where they allow the steam to expand. The reason for that is to get rid of as much mineral as possible so that it doesn't jam up the turbines. Here's what the countryside looks like. You can see it's indeed very remote, very desolate, and unfortunately the day we were there, very wet. The chance of a lifetime to see this kind of thing. There are some of the flash towers that have not yet been installed. I'm hiding in the door of the bus to protect the electronics of the camera, but because everybody was gung-ho and excited to see what the Russians were trying to do, the group of us that were there as guests of the Russian government from the Water Rock Interaction Group, an international group that studies how water and rock react, we're willing to put on our boots and wade through this mucky muck to learn what we could learn about the geothermal energy prospects, geothermal exergy prospects that will happen, as we've just said in the previous footage in Iceland, in the next decade probably in Russia. So with some pride, justifiable, we're seeing another demonstration as we saw at the opening of this tape in Italy, pouring down rain, but they wanted to show us that they had plenty of steam pressure in one of their first wells that they put in the Kamchatka Peninsula. While this looks primitive and is in the middle of nowhere currently, the production of electricity is what you're seeing shoot up into the air, at least the potential for the production of electricity and development of far more energy-intensive industries in the mineral wealth that Russia has not yet exploited. An example of this development of a country, since Iceland has developed so much geothermal energy, they actually bring by boatload some of the aluminum ore from as far away as South America, northern South America, and use the cheap geothermal electricity in Iceland to refine the aluminum. The aluminum being a light metal, they can still afford to ship it back to customers half a world away and make a profit. So energy really does play a role in not just creature comforts in society, but the level of civilization and certainly the level of finance. Again, you can see this looks pretty muddy, pretty desolate, pretty wasted, but a lot of the future of this part of Russia will depend on whether this exergy exercise is successful. And we will visit that with some geothermal energy considerations down through Japan,
on around Wara geothermal field, and the crater and summit of Hakona volcano was another highlight, certainly of WRI-4. Wind is carrying the sound better this way also. The path that Rosemary Vidali is walking on here, we were told by Dr. Secchi, had in fact been just rebuilt in the last 2 weeks because of the instability of the slope here. Later in the morning, as the wind blew some of the fog out of the caldera area, Lake Ashi is down below as a caldera lake, but here at the summit we see some of the equipment being used to try to do the geothermal drilling. Around, even down to North and South Island of New Zealand. Power station, hydroelectric, Aotearoa, and so forth. There's Wairākei and Lake Taupo, and some of the mountains. Here's an elevation diagram showing wattages. Here's Hakuri doing 112 megawatts. Dropping the water down through. Usually a gigawatt if you add them all up. Wairākei at 153 and Oahu at 108 are the geothermal systems. The black are the hydroelectric. And any red ones down here on the flat are actually thermal, meaning fossil fuel. Coming up the valley, there is reinjection here, just newly formed. Typically each steam outlet is separator. Dr. Stuart Simon, one of the principal investigators in geothermal energy in New Zealand, will give us some of the background here at Wairākei.
This was all a consequence of exploitation. The Waiora Formation's a pyroclastic flow deposit with lots of pumice fragments in it. Seems to be one of the main lithologies from which production is sustained. Contacts, lithologic contacts are probably also important, and faults may also be important for permeability here. There, you can see, you can interpret offsets along faults based on displacements of stratigraphy in the older units in the subsurface. Most of the wells originally were drilled to about 500, 600 meters depth, and they tapped about a 250 degree water, and it was a single liquid phase reservoir. And all the flashing took place in the well. Wairakei was the first liquid-dominated geothermal system in the world to be drilled. Exploration started here in 1950, and the power station was commissioned in 1958. and the the New Zealand engineers, along with their help from the UK, designed many of the features that you see on the surface down here. And this is in fact a museum of steam separation strategies that you see before you. And you could spend a whole day looking at different designs on steam separator vessels here in the Wairakei field. And much of the experimentation that was learned from Wairakei experience has been sent overseas, places like the Philippines, Indonesia, Africa, many other countries in the world.
One way to generalize what we've been trying to learn is to look at a graph. In this graph, you see in the upper left corner, we're at the surface of the Earth, and as we come from that corner down to the bottom of the page of the graph, we are going down inside the Earth. On the left side, it's shown going down in thousands of feet. On the right, it's showing going down in kilometers. And across both axes are the temperatures and common scales at the top, centigrade, and at the bottom, Fahrenheit. Starting at the upper left, there is a solid curve, and of course water boils at the surface of the Earth at 100 degrees centigrade, but as the pressure increases, as we go down into the Earth, that's going down into the graph from the top to the bottom, you see that the curve shows that the boiling point of water actually increases from 100 to almost as much as 400 degrees centigrade. That's because pressure put on the water that's trying to boil holds the steam from expanding and being able to boil, and so high pressure causes the water to be much more high in temperature before it will boil. On the graph there is also a shaded wedge starting from the upper left, two lines, one the oceanic crust, which is the one to the right, and one is the continental crust, which is the one to the left of the shaded wedge. That is the way in which temperature increases as one goes towards the heat of the core of the Earth. The screen shows you now where that wedge intersects the solid boiling point of water, and the one to the right is the oceanic crust. You see that that intersects the boiling curve of water at something like 4 kilometers, between 3 and 4 kilometers. But in the continental crust, the bottom arrow is indicating that the solid boiling point of water curve would intersect the heat that's naturally in the Earth, so that water would boil from natural heat in the Earth closer to 7 kilometers. One can even make kind of a joke out of this, and if a societal question is asked, where are we relative to being ready to use geothermal energy, the common answer could be that we're about 7 kilometers away. And what we're joking about scientifically is that we would have to drill about 7 kilometers deep in the continental portions of the world to have the bottom of the well be naturally hot enough for water to boil according to its own properties at that pressure. Having just seen that if we stay away from volcanoes and known really hot spots but play with just the normal Earth, that we may have to go as deep as 7 kilometers to find boiling point of water to make geothermal steam, it behooves us to look at what the cost is of drilling that deep. In this study, the graph is showing data collected from both the United States and from England, and costs involved in drilling fossil fuel wells like oil and gas. And the vertical axis is in the cost in millions of dollars, and the horizontal axis is how deep you can drill for how much money, or well depth for each well. There are some triangles which give the data from actually Britain and some circles which give data from North America. And this is all part of a study in trying to use not volcanoes, not known hotspots, but just hot, dry rock. Go down inside Mother Earth, find a place where the rock is even normally hot, and pour water into the hole and have the steam come back up, perhaps a second hole. Within this graph, there is a straight line, and then there's kind of a shaded hump on that straight line. Some of the uncertainties of what kind of rock you're going to hit. Are there complications? Are there the need to actually put lining in the well? Problematical problems, but the generalization that you've just seen is that it's going to cost about $1 million to drill about 2 kilometers. So each well that would go to 7 kilometers, you can do the math, would be about $3.5 million. And it depends on how much energy you hope to get out of that well over a period of years, whether the taxpayers of whatever country this might be happening in are willing to lay out that extremely high price for a single well. And it may be that you need more than one well. It may mean that you, for a large amount of electricity, need a dozen wells in a given area. So cost certainly becomes a very serious factor in deciding to use geothermal energy. In the hot, dry rock model that Los Alamos Labs and the British government and many others have thought about, as we've just said, they do not attempt to find a particularly hot area in the earth, maybe a little bit hotter than normal, but the idea would be to drill down to this heated area and inject cold water, allow it to boil, and come back up a second hole for accessing steam. So a way of extracting the geothermal energy for power production. Because many of the volcanoes are perhaps too dangerous to play with, and many of the areas like Yellowstone are environmentally and properly so protected, where else could we find hot, dry rock? Where could we find some higher than normal heat? And the map that you're now viewing is a color rendition. Blue in the eastern part of the United States is not very productive because it's not very warm as one goes down. The red spots are in fact hotter spots in the western part of the United States. The red actually, from the legend of the graph, says that it could go as much as 70 degrees centigrade per kilometer of drilling. In other words, as you go down each kilometer, it would go to 70 degrees higher. So those reddish spots, if they are available, not environmentally protected, many considerations in society to worry about with that, but if they were available, those would certainly be the target areas for geothermal exergy exploitation. Again, in the blue areas in the east, there's not much of a target, but that's really the Boston, Washington axis of population, New York City and so forth, Philadelphia, Baltimore, thousands of miles away from one of the possible geothermal areas. On the other hand, on the western coast, California, some possibilities, but there again, blue pervades some of northern California, even though there are some commercial geothermal electric power production plants on the California, northern, southern Oregon border. To transmit electricity more than about 200 miles in existing electric wires loses too much power in the resistance of the wires. So until superconductivity becomes a reality, it may be that geothermal energy is not going to work too well in North America.
the water down around Karen's feet there would be about 75, 76 degrees, but it's discharging up there about 98, 99. And the highest temperatures that we measured last week with the digital thermometer here were about 99 degrees. Okay? So pretty close to boiling. You'll see a lot of evidence of boiling in the springs.